Are we live? Okay. Any questions about anything before we start? Yeah, well, if you've emailed me and I haven't answered you in the usual instantaneous fashion, it's because of this power failure. Okay. So that's why. You emailed me, I didn't know until you told me. Right. So any questions? It's like we have some regulars who come like almost every class, and then we have a bunch of people who come like half the time. It's like you, you know. Do you watch the videos? Yeah? Do you understand this? Does it come through?
Yeah.
Yeah.
I had a lot of practice with Markov chain in high school.
Right. Okay. Fine. No, you don't have to give me an excuse for not. You don't have to, like.
For 3150.
It creates an intimate class atmosphere when people don't show up. You notice it? Okay. Well, today we're going to wrap up the Markov chains and move on to why we're studying Markov chains. So, remember last time we talked about a key, quote-unquote, probability 1 convergence result. And I'm not going to restate that result in its full glory. I am going to restate a special case of it in a minute, because I want to get to the last important convergence theorem that we're going to need, and that is this thing called the Ergodic Theorem for Markov chains. Okay, so before we're gonna remind you of that in a second, but for now, I want to consider the following special case. And the special case is that you've got an irreducible Markov chain. So the Markov chain is irreducible. That is to say, you can get from any state to any other state in finite time. So I goes to j for all j, I and j. And the whole state space S constitutes one big positively recurrent class. So whole state space S constitutes one sort of big positively recurrent class. Now, let me just note that it's possible for the chain to be irreducible, but for every state to be transient. It's possible for the chain to be irreducible, but every state be null recurrent. But if the chain is irreducible and at least one of the states is recurrent, then the whole state space has to be a recurrent class, a recurrence class. And if at least one state is positively recurrent, then by one of our earlier results, all the states have to be positively recurrent. Now, this is in some sense a generic situation. You can take the probabilities and alter them by an arbitrarily small amount and come up with a Markov chain that has these properties. Okay, now in this case, the Markov chain has a unique stationary distribution. Pi star. And for any state j, pi star j is going to equal to 1 over mj, and that's always going to be positive, because everything is positively recurrent. Mj, again, is the mean first return time to state j, ej of tj. Now the question is, how does this probability 1 convergence result specialize to this case? Well, I'm going to give you an even more general version of it, and then I'm going to remind you that one we talked about last time is actually a special case of this. Okay, so I'm going to let f be any real-valued function defined on the state space S. So this is any function that has a finite expected value against this unique stationary distribution, such that, and the notation I'm going to use, e pi star e sub pi star of f. What is that? That's the sum over all states j of f of j pi star sub j. Assume that that's finite. Okay, so f is any function defined on the state space that has a finite expectation with respect to the unique stationary distribution. Then we have the following, the ergodic theorem for Markov chains. In this context, that is to say, for any Markov chain that's irreducible, whose whole state space constitutes one positively recurrent class, and therefore has a unique stationary distribution, if f is any function with a finite expectation with respect to that stationary distribution, the following is true. If I take the sum from m equals 1 to n divided by n of f of xm, where xm is the state of the Markov chain at time m, this converges with probability 1 to e pi star f as n goes to infinity, regardless of what initial distribution you started with. So for any initial distribution pi of 0. So this is probably the most important limit theorem about Markov chains. We're going to be using it again and again as we go along, as you'll see. The point here is, what this does is it relates the long-term average of any function f over runs of the Markov chain, over a run of the Markov chain, with the average of the function f with respect to the stationary distribution. Now, this is in some sense a static thing. It's like a spatial result about f. This, on the other hand, is kind of like a dynamic thing. It's like a temporal result about f. So let me just state in English here, that is to say, the average value, and let me be really explicit about this, the time average value of f along any, and I'll put the word any in quotes because any just means any run except with a set of runs with probability 0 of the Markov chain. The time average value of f along any run of the Markov chain converges as n goes to infinity to the space average of f, where by the space average of f I mean the average of f with respect to the stationary distribution, e pi star f, with respect to the stationary distribution. Okay, so that's the ergodic theorem for Markov chains. And it holds, once again, for Markov chains that are irreducible and whose whole state space constitutes one positively recurrent class and therefore have a unique stationary distribution. And it actually holds for other slightly more general ones, like you can have some transient states as long as they reach this one positively recurrent class. I don't want to go into all those details, all those very fine points about this. Now, you can imagine, this is sort of like, think of this f as, say, for example, every time, if you think about the light wall model, right? Every time the red light flashes, someone pays you $1. Every time the green light flashes, somebody pays you $7. Every time the yellow light flashes, you have to pay 10 to the 59th dollars. You know, you don't want the yellow light to flash, right? But anyway, the point is, if you think of f as being, say, f of j, for j in S, as being some amount of money, a payment you collect, every time light j flashes. Okay. This is something that happens dynamically as you run the Markov chain. Then the average amount of money you collect per unit time in the limit, so the average payment to you per unit time in the limit of a very long run is going to be E pi star f. So that's one way to think about this. And EG means exemplar gratia, is that correct? Actually, I was at a meeting yesterday afternoon, and one of the guys in this meeting is a classics professor, and he was talking sort of offhandedly about how he's going to get to spend the summer in Rome teaching Latin. And I said, hey, here's a good story about Latin. One of my engineering students actually knew what EG meant in Latin. And he said, that's very impressive. That's great, you know. Exempli. Okay, well, now two of my EC students know what that means. Anyway. All right, well, that's that. Okay, so that's the ergodic theorem. Now, why, a minute ago, like I said, I want to revisit the one we talked about last time. Why is the one we talked about last time a special case of this? This is just a sort of an aside. So here's an aside. The earlier probability 1 convergence result in this context, and I mean by the three-word admonition in this context the same thing I mean in the hypothesis of the ergodic theorem for Markov chains. In other words, we're talking about a chain with one big positively recurrent class as a state space and one unique stationary distribution for that reason. In this context is actually a special case. Of the ergodic theorem. Okay, so what does the earlier result say? The earlier result says that nj over n, nj of n over n, the number of visits to state j over the time interval 1 through n divided by n, converges with probability 1 to 1 over mj for all j in the state space S. And of course, this is a much abbreviated version of the earlier result because of the context we're talking about here. The one recurrence class Markov chain. Now, how do we reconcile this with the ergodic theorem? So here's the reconciliation with the ergodic theorem. What I want to be able to do is express this nj of n over n as the sum from m equals 1 to n of some function f of the state xm. So we want to express nj of n divided by n as 1 over n sum from m equals 1 to n of f of xm for some function f. From S to the reals with E pi star of f less than infinity. Now, can anybody suggest a function f that will work here? I'll tell you what it is, don't worry. I won't make you go home and figure it out. What is nj of n? Nj of n is the total number of hits of state j. Yeah?
Do you have like an indicator variable for a given state maybe?
Exactly. He used one word that people use for this. The indicator function of the state j is going to be your f. And I usually call that the characteristic function of the state j, but everybody has a different word for it. So the appropriate f here is what I call chi j. Chi is like a slightly bigger script x. Chi sub the set consisting of j. What does that mean? This is a function from S into the reals. Chi j of I is equal to 1 if I equals j, and 0 if I is not equal to j. And this is known as the characteristic function, chi j, or indicator function. And chi is supposed to stand for the ch in characteristic. Like there's a Cornell a cappella group called the High Notes. I don't know if you ever heard of them. They pronounce it that way. They spell it like chai, the drink. And their specialty is like klezmer type, songs or something like that. So chi is the actual first letter of that word. Or indicator function of the set consisting of the state j. It's 1 for everything in that set and 0 for everything outside of that set. And note that the expected value of chi j with respect to the unique stationary distribution, pi star, is what? What is that? If the unique stationary distribution pi star is anything, what is e pi star of chi j? It's 1 over mj. Well, first of all, let me just say it's pi star sub j, which happens to be 1 over mj. And that's less than infinity. So we are OK to use the ergodic theorem on this f, this chi sub j. The bottom line here is that nj of n is just going to equal the sum from m equals 1 to n of chi sub set j of xm. Therefore, 1 over n, nj of n, is equal to 1 over n times this sum. And 1 over n times that sum is going to converge to e chi star j, which is 1 over nj. So let's just finish this up. Do the 1 over n thing. This converges and go to infinity with probability 1 to e pi star of chi j, which we just discovered is 1 over mj. And thus, the earlier result is a special case of the ergodic theorem for Markov chains. All right? Okay. Now, I want to wrap up this part with two things. First of all, I want to talk about the special case we were talking about, a finite state Markov chain, because that's, of course, the one of primary interest to us. Does everybody sort of get this, pretty much? You shaking your head no?
I lost it.
Okay. Tell me where.
Right there.
Right here? If you have a real valued function on the state space, then you can take its expected value against the stationary distribution and get that. Right?
Isn't the stationary distribution kind of like the expected value?
The stationary distribution is just some distribution on S. And if you think of f as any function defined on a set that has a probability distribution on it, is going to have an expected value against that probability distribution.
So like an arbitrary f.
This is an arbitrary f. It's any function with a finite expectation against that stationary distribution. And that, in some sense, that expectation is what I called here the quote-unquote space average of f. against pi star. And the ergodic theorem relates the time average of f along typical paths, typical runs of the Markov chain, to its space average across the state space. And those things one would have no a priori reason to expect to be the same, to equal each other. But they do. And that's a cool thing. And that's a very useful thing as it happens. Yes?
Can you give an example of the function over the state space?
How about the state space has two things in it, 1 and 2. F of 1 is equal to 17, and f of 2 equals 23. I'm sorry?
I mean, so...
You can think of it, like I said, if you want, f, a function defined on the state space, you can think of as a payment that you collect every time the Markov chain hits that state.
Okay, and is this function supposed to, like, tell us anything special?
Later it will. When we talk about the Metropolis algorithm and stuff, it'll be things like, if you're doing a problem in physics and you want to figure out what say, pressure do you expect to find this system in? If someone comes up to you in a whole plaza and hands it to you, that kind of thing. It's going to be the expected value of some function against something called the Boltzmann distribution. In this case, this chi-j case, if you use the payments analogy, you can think of chi-j as every time light j flashes, somebody pays you $1 exactly, right? And you don't get any dollars if any other state flashes. Over time, over the long haul, how many dollars per unit time are you going to make? Well, that's going to turn out to be 1 over mj. Now, why do you expect that? You expect that because if mj is big, that is to say, if it takes a long time on the average to return to state j, you're not going to be collecting $1 very frequently, right? Whereas if mj is small, if you're going to get back to j pretty quickly, then yeah, you're going to be collecting money quite often. Yes?
What if there isn't a single stationary distribution? Can we say anything about your expected value?
You can, but I don't want to go there. It's just, like I said, you can extend this result. You can talk about, like, if you have one positively recurrent class and some transient states, or you can talk about where you have multiple positively recurrent classes and some transient states. You could talk about this in terms of the probability that you hit a given one, all that kind of stuff. But those are all like refinements that we're not going to need. Matt?
I'm missing the link. Like, what gives you, I guess, the right to apply that to the Markov chain? Like, is there some property that has to be satisfied?
It's all this in this context. The context being the Markov chain is irreducible. Its whole state space constitutes one recurrence class, and it's positively recurrent, and therefore the Markov chain has a unique stationary distribution by our early results. And the function you're looking at has a finite expectation with respect to that unique stationary distribution. All those things have to happen. That's what these 3 words are meant to summarize. Okay? And again, over here, I use those 3 words somewhere. Here. Anything else about this? It's all in the handout, but I'm trying to give you the highlight reel in class, so of the things we really need, and this is the one we really need. And the problem is, to get to this one, we have to go through all this other stuff. We have to understand what recurrent states are, what transient states are. We have to understand all that stuff just to get to this one special case and understand why it's true. Okay. All right, so 2 more little things, like I said. One is what happens when you have a finite state Markov chain. So here's a special case. So suppose you're dealing with a finite state Markov chain. So the state space S is going to equal, say, 1, 2, up through capital M for some finite positive integer, capital M. Okay, now what can you say about this situation? It turns out, and there are proofs of these things are in the handout, and I can give you hand-wavy arguments for at least a few of them. First of all, it turns out that there are no null recurrent states. And the reason for that is you can prove that if you have a null recurrent state and you look at its recurrence class, that recurrence class has to contain an infinite number of states. And therefore, if you have a finite state Markov chain, and therefore you can't have an infinite subset of that state space, you can't have a null recurrent state. Matt?
Are we still in this context?
No. So that's part of why I put that line there, to separate mentally. We'll get back to this context in a minute, though. Okay, so you have no null recurrent states under any circumstances. Second of all, you're always going to have at least one positively recurrent state. And if you reflect on 2 in the light of 1, 2 is the same as saying you can't have all transient states. Okay. That is to say, not all transient states. Any Markov chain, all of whose states are transient, has to have an infinite number of states. Okay, these are easy to prove. That if you have a finite state Markov chain, you have no null recurrent states and at least one positively recurrent state. Now, because of 2, we have item 3, you have at least one stationary distribution. Pi bar. How come? Well, last time one of our results was that when you have a Markov chain, associated with every positively recurrent class is a stationary distribution concentrated on that recurrence class. And since you have at least one positively recurrent state here, you have at least one recurrence class, positively recurrent states, therefore at least one stationary distribution. You can have more than one, but you have at least one. Okay? Now, what kinds of stationary distributions can you have? What are they, algebraically speaking? If you define the matrix, the M by M matrix, capital P, and I think I put an underline under that just to indicate that I'm talking about a matrix, by means of the formula capital P sub ij equals ununderlined P of ij for all I and j between 1 and m. In other words, you take all the transition probabilities and you put them in the natural way into an m by m matrix. Then any stationary distribution pi bar satisfies the following equation. Pi bar matrix P equals pi bar. And you're thinking of pi bar here as a row vector, pi bar sub 1, pi bar sub 2, up through pi bar sub cap m. And that's just the defining condition for a stationary distribution. No. If you think of distributions, I've been trying to enforce the row vector interpretation of distributions. Got it? Yeah. So this equation, this is something I like to do with vector matrix equations to sort of do a reality check, is draw a little picture of what it looks like, vector matrix wise. That's what it looks like. Okay. Now, what is a vector that has this relationship with the matrix P called? Yeah, it's actually a left eigenvector of the matrix P, corresponding to what eigenvalue?
Wow.
Yeah. So that is to say, the stationary distributions are all the left eigenvectors of P, at least all the ones whose entries are non-negative and sum to 1, corresponding to eigenvalue 1. So thus, any stationary distribution pi bar is what we call a left eigenvector of matrix P, corresponding with eigenvalue 1. And so you can solve for these things. You can solve for all the stationary distributions just using algebra. You can just sit down with those linear equations and the constraints of non-negativity and add summing to 1 and find all the possible stationary distributions. Cool. Okay, now we go back to in this context. Okay? So, what if the Markov chain is irreducible? So if the Markov chain is irreducible, then what do we know? What do we know necessarily? Well, we know that it has no null recurrent states. We know that it has at least one positively recurrent state. And because it's irreducible, that means you can get from any state to any other state, which means that every other state, other than this one positively recurrent state, is also recurrent and lies in the same recurrence class as that original state. And therefore, the whole state space automatically constitutes one big positively recurrent class. And thus, a unique stationary distribution. There's only one stationary distribution exists. So this computation of stationary distributions will lead you to one answer only. And we can compute it by algebra from pi star p equals pi star. And by doing that, what we'll actually find each pi star j that way. But what do we know about the pi star j's? Pi star j's are just 1 over mj's. And where did the 1 over mj's come from? The mj's came from addressing dynamical questions about the Markov chain. How long on the average does it take to get back to state j, given that you started at state j? So let me just put up a little schematic here, a very little schematic. And this, of course, is true for arbitrary infinite state Markov chains that have one positively recurrent class as their state space. But the point here is that pi star j, you can compute from sort of static linear algebra. And it's equal to 1 over mj, which comes from probabilistic dynamic behavior of the Markov chain, at least in terms of computations. And I think that's kind of cool. You know, you have this static thing going on, and you have this dynamic thing going on, and they're equal. All right. Now, I think somebody last time asked, and maybe it was after class, asked, like, if you think about the marbles in the bins, right? There's two. Remember, there's two. If you weren't here last time and didn't read the handout, not to single you out, Rishi, but anyway, there are at least two ways to think about Markov chains. One way is the light wall, you know, with the operators, and the other way is the marbles in the bins, where people reallocate their marbles. And we need to think about the marbles in the bins model in order to understand the notion of a stationary distribution, at least IMHO. Okay. Now, the thing is that somebody asked, all right, in the marbles and bins model, right, does the distribution of marbles settle down to a stationary distribution over time? In other words, say you start off and one dude has all the marbles in his bin, and then they start spreading out among the bins. Will they sort of level out to a stationary distribution as time goes by? How many people think yes, they will? Absolutely. How many think that they will sometimes but not other times? That's the safe answer. Okay, good job. Well, that's true. It turns out that sometimes, so this is the final question, and I'm not going to, since it's not of that much interest to us in this course, but if you take, say, EC 4110, then this will be the main focus of their Markov chain discussion. It's like, when do distributions actually converge? So here's a final note, or a final question. Let's pose it as a question. Given a Markov chain, okay, that has at least one stationary distribution, and let me put a double line here because we're now back to the general case of infinite Markov chains here. So given a Markov chain with at least one stationary distribution, when is it true that given pi of 0, pi of m, or pi of n, which you get from this recurrence relation, pi j of n plus 1 is equal to the sum over I in S of pi j, or pi I of n, p of ij, for all j in the state space S. So that's a recursion relation that gives you this distribution of marbles in the bins at time n plus 1 in terms of the distribution at time n. When is it true that pi of n converges as n goes to infinity? Converges at all. And when, in addition, is it true that the limit is a stationary distribution? So moreover, if it converges, does it converge to a stationary distribution? That's a legitimate question to ask. And you want to think about a picture. Think about the marbles settling down to some kind of static allocation. The green one will still be bopping around from bin to bin. That's the state of the Markov chain evolving. But when does the actual distribution of marbles level out over time? And it turns out that there's a condition that guarantees that. And it's especially relevant when you have the generic case, the in this context case, where you have one big positive recurrent class as your state space. So here's the answer. The answer is that it turns out that pi of n will converge to a stationary distribution provided the Markov chain satisfies a condition called aperiodicity. And I'm not going to go into that. I'm just going to give you an example of why we need it. So if the chain is what is called aperiodic, then pi of n will always converge to a stationary distribution. And what stationary distribution it converges to will depend in general on the initial distribution. So what stationary distribution it converges to depends on pi of 0 in general. But if you have only one stationary distribution and you have that generic context, so in the quote-unquote generic context, that is to say irreducible, and one big positively recurrent class, like we needed for the ergodic theorem, in that generic context, it converges to pi star, the unique stationary distribution, for all pi of zeros. So no matter what pi of 0 is, pi of n goes to pi star as n goes to infinity, in case the chain is aperiodic. Now, like I said, I'm not going to tell you the whole story on aperiodicity. It's in the handout, whatever. What does aperiodicity rule out? Okay. You know, I don't know if you heard me at the beginning, but they took away the nice eraser that we had last time with the little guy on it. Remember? Now, I'm wondering if you guys are hiding it out there somewhere. And you knew that I like that eraser. And not sure I believe you. This one is pretty good, but it doesn't have the cute picture on it. So what does aperiodicity rule out? It's needed to rule out things like this. Okay, I'm going to put up a really trivial two-state Markov chain on the board here. Okay. Now let's go through this. Let's test your knowledge of terms. Is every state recurrent? Is every state positively recurrent? Is the whole state space one big positively recurrent class? Does the chain have a unique stationary distribution? It doesn't? Doesn't a Markov chain have a unique stationary distribution every time its whole state space has one positively recurrence class? Yes, it does. It does. It's every positively recurrent class in a Markov chain has a unique stationary distribution concentrated on it. And therefore, if the whole state space constitutes one big positively recurrent class, well, it's not very big in this case, but anyway, it has a unique stationary distribution. Hazard a guess as to what that is? A half. So pi star is 1/2, 1/2. If you have half the marbles in bin 1 and half the marbles in bin 2, what happens at time 0? Bin 2 guy gives all his marbles to bin 1. Bin 1 gives all her marbles to bin 2. There you go. So half and half persists, but which bin the green marble is in just alternates in a very periodic fashion. No other distribution is stationary. Like, for example, if I have no marbles in bin 1 and all the marbles in bin 2 at time 0, what happens? All the marbles go to bin 1, and then they go back to bin 2, and then they go back to bin 1. So pi of n bops back and forth between 1, 0, and 0, 1. So if, for example, pi of 0 equals 1, 0, then the pi of n sequence is just this. Pi of n is equal to 0, 1 if n is odd, and 1, 0 if n is even. And certainly a thing that bops back and forth between 2 points that are far apart from each other doesn't converge, so fails to converge as n goes to infinity. So that's essentially what you need to rule out by aperiodicity. And it all has to do with the greatest common divisor of something being 1, and there's number theory involved, whatever. But under that assumption that rules out situations like that, you have this distributional convergence. Okay? All right, so that's the wrap-up of the general discussion of Markov chains. Anybody want to ask any question? I know you probably haven't processed it all on the fly. When you sit down and work at the problems, you'll see nuances you probably didn't see before, which is good. And also, by the way, when you read the homework solutions, I'm deliberately writing detailed solutions, so reading them will be, I hope, somewhat of a learning experience as well. Have a question? You're not sure, Randy?
Could you explain one more time, what is the aperiodicity assumption?
I'm not going to tell you it because it's too complicated, but it's needed in order to rule out this. Okay? This is like the most trivial periodic Markov chain situation. All right, I'll tell you what, just as a special treat for you and Shane, I will state the aperiodicity assumption. For every state j, the greatest common divisor of the set of all m values for which p superscript m of jj is positive equals 1. That's it. What's that? They're not all coprime, but taken together they constitute a mutually coprime set. Yeah. Mohammed.
In this example, do we have 3 stationary distributions, half, 0, and 1?
No, because 0, 1 doesn't persist. It goes to this. Stationary distribution has to persist. Right? We have a unique stationary distribution, but the distribution at time n does not converge to it as n goes to infinity because of this periodicity phenomenon. That's the point. Anything else? Oh, why don't we take the 3-minute break now and you can think about Rishi.
This is like kind of an unrelated question.
Mm-hmm.
And you actually said my name right the first time.
Rishi?
Yeah, fun fact.
Okay. Because I know Shiva likes Shiva as opposed to Shiva.
Yeah.
Whereas in school we learn Brahma, Vishnu, and Shiva, so I suppose
Yeah, I really don't care.
I'll try to say it right from now on. Okay.
Is the 1/2 related to like Grandi's series?
Related to,
0, 1, 0, 1, or you sum that up? It's
well,
kind of an unrelated question. I was just like wondering, like, is it the average value, or is it the like the sum of or like the partial sum of the series convergent? Like how
one way to get it is to look at the transition matrix for this Markov chain, which is this, and try to compute a left eigen. What are the eigenvalues of this matrix? 1 and -1, right? So try to compute a left eigenvalue vector, pi1, pi2, star, star, corresponding to eigenvalue 1. And if you write out these equations, what do they say? They say pi1 star equals pi2 star, and pi2 star equals pi1 star. They're always going to be redundant. But the only way to have pi1 star and pi2 star be the same and be non-negative and sum to 1 is for them both to be 1/2. Got it? So that's the algebraic way of seeing that. And you can see it dynamically by figuring out trivially, what the MJ is for each of these states. It turns out to be 1/2. You spend half the time in state 1 over the long haul on the average, half the time in state 2 over the long haul on the average. Okay, so let's take the 3-minute break, and if you think of any other questions you want to ask about this general stuff, fine. We can talk about those, and then we'll move on to the next little segment, which is the Monte Carlo / whatever stuff. What do we do with this stuff? What do we want to do with this stuff? Well, okay, are we back live? Yeah. First of all, Markov chains are so important and so useful in all branches of, engineering and mathematics and whatever, that I'm hoping that you take away from this, plus the handout, you can learn more about them in the future if you need to, based on this very sketchy introduction. Okay. Not to sandbag, but to sandbag. Okay, so what are we going to do with all this? It turns out that the proofs of all the probability 1 convergence stuff that we talked about depend on a really important result from probability theory. So the proofs of all the probability, and I'm not going to show you in class how they depend on this. You can see it in the handout if you want. Probability 1 convergence results all those proofs hinge on a result from probability theory called the strong law of large numbers. Now we did this, we talked about this in 4670, right? Folks who took this briefly? Okay, this is known as SLLN colloquially, which I always wish that were a Roman numeral, but because it has 2 L's and it makes me think it should be, from probability theory. And how does that go? It's hard to prove at this level. In fact, it's nigh impossible to prove at this level. And I know it's scary, but there's no reason to leave because of it. Here goes. Suppose that, say, Z1, Z2, Z3, ... These are a bunch of random variables that are independent and identically distributed and another common math abbreviation for the situation is IID, lowercase, for whatever reason. So these are independent and identically distributed, either discrete or continuous valued random variables. With a common finite mean, z bar. And it has to be common to all of them because they're identically distributed, right? If you have random variables with the same distribution, they have the same mean. Common finite mean, finite expected value. Let's call it z bar. Then the following is true. With probability 1, if I take 1 over n times the sum from m equals 1 to n of zm, which of course is just z1 plus z2 plus zn divided by n, this converges as n goes to infinity to z bar. That's the strong law of large numbers. And a way of writing that in sort of fancy probability talk is probability that the limit as n goes to infinity of 1 over n times the sum of the z's between 1 and n, probability that that is equal to z bar is 1. So that's the formal way of saying that they converge with probability 1 to z bar. And again, this is a relationship between time averages and space averages. Space average is like the expected value of z bar. The time average is like what would happen if you drew a sample of each of these things, one after another, and just summed them up, tabulated them and summed them up over time. A typical such sample sequence will converge to z bar. By typical, I mean all sample sequences except for a set with total probability 0. That's the strong law of large numbers. And like I said, I'm not going to tell you how these results depend on it, but you could read about it in the handout. Okay, so this is an important result, and this has been known for quite a while. This is from early 20th century, Kolmogorov and people like that, the founders of measure theoretic probability. And it's an important result from probability theory. Now, back in the 40s, back in the 1940s, was when the first, the sort of the great granddaddy of all sort of random algorithm / random search stuff started to bubble up. And the reason it started to bubble up was that all of a sudden we had computers. We had actual machines that could do computations. Now, does anyone know, like before, say, 1945, people used the word computer a lot. What did that mean? Does anyone know what that means? Yeah? A person who sat and did arithmetic, exactly. Now, at Los Alamos was where they built a lab out of the desert to make an atom bomb, right? But after they were done with that, well, we'll get to that in a second. The computers at Los Alamos were people. In fact, they were actually women. They were all women, okay? And they sat together in a big room with adding machines, literally, doing these computations. Like Hans Bethe or Edward Teller would come in with some computation to do and give it to these people to do. And sometimes, remember there's more than one computer. There's a whole bunch of them. Sometimes Hans would say, well, I can actually do this computation independent of this computation, so I'm going to divide the computation that way, and I'm going to give this one to one computer and this to another computer. What was that an early example of? Yeah, parallel computing, right? So anyway, parallel computing was also invented then. But really what it meant was giving one woman, literally, a computation to do, and another woman another computation to do. They weren't allowed to do the science. But we'll see later that two of the co-authors on this important paper are both women. Okay. But anyway, so that's what computers were. But in the mid-40s, okay, in the mid-40s, and I have to say 1940s because pretty soon I'll be teaching students who were born after 2000, and that's pretty frightening. Pretty frightening to me. In the mid-1940s, the first electronic computers, so the first computing machines, not adding machines, but so bigger than, say, adding machines, which were around for a long time, arrived on the scene. Okay? And, John von Neumann was one of the first guys to build these things. There's a great history of where these came along. And some of the, okay, so after they were done making the atomic bomb at Los Alamos, the scientists decided, hey, this is kind of a nice area of the country, if you've ever been there, if you've ever been to Santa Fe, it's like it feels very mystical out there, Last time I taught this class, there was actually a kid in the class whose father is a physicist at Los Alamos. And so he enjoyed this part of the conversation. But it's a very kind of mystical place out there. And so it was very attractive to some of these scientists and mathematicians who had been there for the atomic bomb, so they just decided to stay there. And Los Alamos lab became a lab that did a lot of other stuff besides make bombs, although that's still sort of what they do, by and large. So some of the mathematicians at Los Alamos, and in particular, one guy in particular, Stanislaw Ulam, he was a Polish mathematician who actually, he's sort of a highlight of this whole discussion, and others became intrigued by the possibility of using these new fast computing machines and their inherent ability to generate pretty good sequences of random numbers to do difficult calculations that involved random variables. Okay, so they became interested in using these new computers to do complicated, and we'll see examples of these complicated calculations, physics types calculations. So became intrigued by the possibility of using computers, physics type calculations by exploiting the computers. First of all, speed. Ha ha ha. You can imagine what speed meant in 1945, right? No, I'm not talking about the drug or anything, but no. What were you laughing about? Like computers' speed and ability to generate sequences of random numbers. And I won't go into how they do that. There's all kinds of ways they can, whatever. But he was thinking, wouldn't it be cool if we could do, and why would this be important? Why would the random thing be important? Because a lot of the physics problems they wanted to solve, let me put a little asterisk here, a lot of the physics problems they wanted to solve came from statistical mechanics. And we'll talk a little bit about statistical mechanics later on, but the idea of statistical mechanics is you have this impossibly large range of possibilities, and so really all you can ever hope to do is get sort of an idea of the probability that you'll find a system in a certain state or another, or the expected value of some physical quantity associated with a system that might be in one state or another that you can't determine. And anyway, that's why random numbers were going to be important to them, the ability of computers to generate random numbers. Okay, so the circle of methods that came out of Ulam and company, the sort of the family of techniques, Ulam et al. What does the al stand? I know et means and all the, I know what it means, but we're looking for the Latin here. Et alus, or whatever. Ulam et al. Developed are all known as, roughly speaking, as Monte Carlo methods of various kinds. And the reason they're named Monte Carlo methods, Ulam actually named them this. Okay, so the name is at least attributed to Ulam. And part of the reason that Ulam named it that was that he was one of the, he was like, the modern engineering kid, like Randy, for example. I know this from Facebook, okay? Loves to play computer games, right? Okay? And he's always talking about, oh, the new version of whatever just came out. And, oh, it's too easy, or oh, it's too hard, or whatever. Can you rip me a copy of whatever? But back then, the only games that mathematicians could play were things like gambling. They go to a casino and they, play the roulette wheels, they play blackjack, whatever. They try to beat the odds. And it's all very cool because, it's just like engineering kids today. They like play these video games and they're using their analytical minds and engineering insight. And he loved to go gambling. And so Monte Carlo was where the big casino in Europe where all the rich and famous went to gamble was. Okay. And so that's why Ulam named them Monte Carlo methods, allegedly. So I want to go through a couple of examples of how this comes up, some really simple examples, and then we'll move on to the big part, the core of it. Get this quiet eraser. And the Monte Carlo methods all depend essentially on the strong law of large numbers. So these all depend on two things. One of them is the strong law of large numbers, and sort of as an accessory after the fact, the ergodic theorem for Markov chains. Okay. And the early Monte Carlo methods just depended on the strong law of large numbers, as we'll see. The later ones depend heavily on Markov chains, and the reason why they're better is that Markov chains give you sort of a recursive way of performing certain computations. We'll get to that. Okay. So let's go over some really simple examples. Here's some simple examples. So here's a problem. You have some function g, say, that's defined on the unit interval and takes on real values. Right? Everybody familiar with this notation? Again, it's a 3250 thing. So if you didn't take that class, whatever. If you're given a function g, what you want to do, a really complicated function, you want to compute integral from 0 to 1 of g of x dx. You just want to find that, right? And when I say it's really complicated, I mean it doesn't, you can't do a trig substitution. You can't do partial fractions by Zen or otherwise and separate it into things that integrate to logs. You can't, none of those special cases work. Okay? So you can't compute this thing analytically. So G is complicated enough that you can't sort of integrate it in any kind of a closed form. Okay, so what's the Monte Carlo solution to this problem? The Monte Carlo solution is the following. You use a computer, or whatever, to generate a sequence of numbers between 0 and 1 chosen with respect to the uniform distribution independently of each other. So you use a computer to generate samples, and these are independent and uniform on 0, 1. And I'm going to call those x1, x2, and so on and so on. So you can think of x1 and x2 and so on as being either the sample record of a bunch of IID uniform random variables or as those uniform random variables themselves. Okay. Now, if I let z, say let zn equal g of xn, then zn, z1 through z2, and so on, will be IID random variables and what is the common expected value of these going to be? What is it? Matt?
Let's see, what is, sorry.
Okay.
I'm premature on it.
Okay. All right.
The z bar is like the mean of z of n as n approaches infinity.
No, z bar is the mean of each of those. Think of the x's as being uniform random variables on 0, 1. Okay? Think of, say, x1 as a uniform random variable on 0, 1. x2 is another uniform random variable on 0, 1, independent of x1. G of x1 is a random variable. Okay?
G of the expected value of x. Yeah.
Well, it's just going to be this. It's going to be integral from 0 to 1 g of x dx. If this is the mean of the random variable that is g of a uniform random variable on 0, 1. Okay? And the strong law of large numbers says that if I take the samples x1 and plug them into g and form the z's, so the limit as n goes to infinity, and I know I'm running a little bit over time today, I apologize for that, sum from m equals 1 to n of zm, that's just the limit as n goes to infinity of 1 over n, sum from m equals 1 to n, g of xm equals z bar with probability 1. So to calculate the integral of g of x dx from 0 to 1, which I cannot do in closed form, what I do is I draw a bunch of samples from 0 to 1 independently and uniformly on the interval using a computer. And I just do that kind of, I plug them into g, sum them from 1 to n, divide by n. That average will converge with probability 1 to the thing I want to compute. That's the simplest example of a Monte Carlo method. This is Monte Carlo integration of a complicated function. Now, I'm seeing a lot of mystified looks in the class. I'm thinking of this as a rather simple example, so maybe we'll have to redo it at the beginning of next time. But anyway, send me a one-word email, mystified. No, don't do that. I get too much email already.